the mean value theorem. This section is going to go pretty quick. We're going to discuss a couple different theorems and explain how they're useful going forward. First, we'll discuss Rolle's theorem. Rolle's theorem essentially guarantees a critical point exists for a special type of function. And the function doesn't actually have to be that special. So here I have a graph of a function that meets the criteria. The function is continuous over a closed interval from a to b. So let's say that we're looking at the interval a to b. It's differentiable, which means we don't have any corners or vertical asymptotes. And lastly, it has the endpoints at a and b with equal y values. So the left endpoint and the right endpoint, they have the same y values. Rolle's theorem says for a function that meets those three criteria, continuous, differentiable, and equal y values at the endpoint, then they're guaranteeing that there is at least one c value in between a and b, such that at that c value, so c is the input, the output would be f at c. That's what that point is at the top there of our hill, saying that's a critical point. And we know that critical points have derivatives that are equal to 0, or a horizontal tangent line. So Rolle's theorem tells you that for a continuous differentiable function with endpoints at equal y values, we can guarantee a critical point exists in that interval, meaning that the derivative is equal to 0 at that c value that we found. Now this is true for the picture that I've drawn. We could flip this picture on its head, or we can actually add more squiggles. So in each one of these cases, we are defining our function on some closed interval a to b, and we're able to find a c value within that interval that gives us a derivative equal to 0. In this last picture, we actually have multiple values of c, so I'm going to denote those with subscripts like c sub 1 and c sub 2. So at the c value, c sub 1, we have a horizontal tangent line, and the same for the c sub 2. So Rolle's theorem guarantees a critical point within this interval so long as the function is continuous, differentiable, and equal y values at the endpoints. Now something else to add to this, setting us up for the mean value theorem, is that each of the blue dashed lines that I've drawn have the same slope. So regardless of which picture we're looking at, they each have the same slope. They're horizontal lines, so they all have a slope equal to 0. And something that's pretty neat is Rolle's theorem is guaranteeing that there exists some point c within our interval from a to b, such that when you plug it into your derivative of your function, that the result is 0, meaning the tangent line is parallel to this blue dashed line. So Rolle's theorem is guaranteeing that we have a critical point, and what I'm saying is we can interpret this in another way, saying that the slope of our tangent line is equal to the slope created by the left and the right endpoints. Well, that's exactly what the mean value theorem says. Now, in Rolle's theorem, the endpoints had to have equal y values, but in the mean value theorem, we do not have to have that. We still need to talk about a continuous function and a differentiable function, but now we're saying that the endpoints could be at different y values. So I have a slightly different picture of an upside down parabola. Notice that the endpoints at a and b are at different values. So our left endpoint that's A, f of A. Our right endpoint, that's B, f of B. And in this case, f at A is not equal to f at B. Well, since we don't have that condition, we can't use Rolle's theorem here. Instead, we'll use the mean value theorem, which tells us that we can create a line through our endpoints, and that line is going to have the slope that looks like, so the slope of our blue line looks like f at B minus f at A divided by B minus A. That's just the slope between 2 points. So the mean value theorem says that whatever the slope of that blue dashed line is, there exists a point C inside of that interval from A to B, such that when we plug that C value into our derivative, it creates a parallel tangent line. So just like Rolle's theorem, except for we're not saying the derivative is equal to 0 at this C value, we're saying the derivative is equal to the slope created by the endpoints. And so that statement is written here mathematically. F prime at C is equal to the slope calculated between A and B. And this would be true even if our parabola were upside down or if we had a function that had multiple wiggles between the endpoints. So the mean value theorem basically says that we can find a tangent line that's parallel to the line created by the endpoints of our function. Now the purpose of talking about the mean value theorem really is so that we can talk about this corollary. This corollary tells us that we can use the mean value theorem to determine when a function is increasing and decreasing. Now, we've done this before with looking at a graph. We can identify when the function value is increasing and when the function value is decreasing, but this makes it more formal. So we have, again, a function that is continuous and differentiable, and we're talking about a specific interval from A to B. Part 1 of this corollary says that if the derivative is greater than 0, then f is increasing. If the derivative is less than 0, then f is decreasing. So we're using the derivative to calculate the sign of the slope. Positive slope, increasing function. Negative slope, decreasing function. Now, slope is specific to a linear function. This generalizes to any type of function. So if we start off with a polynomial degree 5, for example, the derivative is a polynomial degree 4. So that polynomial degree 4 doesn't really have a slope, but the derivative is going to be either positive or negative, and we can use that to decide where the function increases and where the function decreases. So we're going to use the mean value theorem to show where the derivative is positive and where the derivative is negative, and then we can use that to classify maximums and minimums of a function, and that's what we're going to see in the next section.